Well, it is a great pleasure to introduce a friend of IMSA, Institute for Mathematical Science of the Americas, and he's part of this fantastic group of mathematicians in the beautiful city of Oaxaca. You have to visit. I was just there last week, and in the beautiful city of Oaxaca, they have this group of young, brilliant mathematicians, starting very strong group in geometry, topology, and algebra. And well, Alfredo is an expert. He comes from the long tradition of representation theory of UNAM. And then he studied with under Keller in Paris. But then he has transcended his algebraic roots and become quite a geometer himself, and doing some beautiful mirror symmetry and many other things. So he's one of the young, rapidly rising stars of Mexican mathematics. It's a pleasure for me to introduce him. So Alfredo Nájera will be speaking from UNAM, Oaxaca, will be speaking on the deformation theory for finite cluster complexes. Alfredo, the floor is yours.
Thank you very much for the wonderful introduction, Ernesto. It's really very nice from you. And thank you to Ludmila and Ernesto for inviting me to take part on this workshop. Actually, presentially, for me, it's like a big regret not being able to be there. I was planning to be there, but due to visa problems, well, I have to get my talk from my office. So I'm very sad about that. But anyways, thank you again. So I'm going to talk about a project that's already under archive, joint work with Nathan Ilton from Canada and Hipólito Terfinger from Argentina. Okay, so the aim of this project, it's actually to build a geometric relationship between two pieces of algebraic combinatorics and draw some consequences from this geometric relationship. So what are these pieces of algebraic combinatorics? Well, cluster complexes and cluster algebras. So as their name suggests, these objects are already related. They are related within the formalism of cluster algebras, but we would like to, somehow the aim of this talk, it's kind of to bypass all this formalism of cluster algebras and just build a geometric relationship between some simplicial complexes and some algebras or some cluster varieties. Well, that's one motivation, somehow to bypass the cluster combinatorics. And maybe another motivation is to generalize these constructions beyond the cluster case. So let me just very, very briefly just elaborate what do I mean by this. So up to Morita equivalence, all finite dimensional associative C algebras are given by a quiver with relations. So, well, I'm working with C, but I could just work with an algebraically closed field, or through this talk of characteristic 0 is better. And what do I mean by the cluster case? Well, when this algebra A, this associative algebra A, is actually 3 Calabi-Yau in the sense of Ginzburg, well, then this algebra is actually given by a quiver with potential. That's something that Ginzburg showed. And to this quiver, we have two pair of varieties, the cluster varieties, which are mirror cluster varieties in a certain sense. So this is work of Fogg-Goncharov. And the question that has been addressed in representation theory of algebras is if there's a similar picture beyond this cluster case. So if we can start with some associative algebra and somehow build some mirror spaces. Well, I'm going to talk about, I'm going to go back to this point quite at the end of the talk. So for the main part of the talk, I will just talk about this relation. So I will have to give a brief introduction to what's cluster complexes, what's cluster algebras, and how we use deformation theory to link this. I'm very aware that maybe a big part of the audience is not an expert on cluster algebras or cluster theory, so just please stop me and ask questions at any point. So okay, so what's the overview of the talk? I will start with a quiver. So a quiver is just going to be a directed graph. And associated to this quiver, there's going to be something called the cluster complex. This is just a simplicial complex in the sense of algebraic of topology. And associated to this quiver, I can also construct an affine variety or a partial compactification. Of a cluster variety. So this is going to be my affine variety is going to be spec of a commutative algebra, finitely generated and everything. And well, the cluster variety, say, in the sense of Fogoncharov or Gross-Hacking-Gil-Kontsevich will be just some open part of this affine scheme. So that's why it's a partial compactification.
The toric situation is included here. Is the toric situation a limit of this situation? Or?
Well, yeah, I mean, yeah, there are going to be toric degenerations to toric geometry. I mean, toric varieties are going to be cluster varieties in a trivial way, I will say this, but and in that case, my cluster complex is going to be very trivial. So I think for this talk, the toric picture is not going to be quite, I mean, the link to toric geometry is not going to be quite as robust as, for example, in the work of Gross-Hacking-Gil-Kontsevich. So there are going to be some similar ideas. I will mention this when it comes to. There are going to be lots of torus actions. That's for sure. That's what I mean. So yeah. And we can go to the toric case by toric degenerations. I will comment on this throughout the talk. So what we're going to assume is that this simplicial complex is going to be finite. So in general, there are lots of quivers for which this is not the case. So it's just a subclass. And in this case, there exists some other cluster algebra or some cluster variety with universal coefficients built by Fomin and Selevinsky, and this has a universal property, but it's somehow referring always to the cluster combinatorics. So our aim is somehow to shed a little bit of light on this object, like from a geometric perspective, and have the following picture. So essentially, this diagram will summarize kind of the idea of my talk. Under my assumptions, we will have the following. This cluster variety with universal coefficients is just going to be a restriction of another family. This family is way more geometric. This is a family just of whose base it's a certain Hilbert scheme. Actually, it's a multigraded Hilbert scheme that only depends on the cluster complex. This is the universal family, and well, this is essentially just a pullback or a restriction of this family to some part of the base, and this part of the base actually arises like a partial closure of a torus orbit. So there is going to be a big torus acting everywhere in this diagram, and somehow this is going to be just a partial orbit closure. Partial closure of a torus orbit. And big torus, it's I mean, the dimension of this torus is going to be bigger than the dimension of many of these spaces. That's why it's not really like in toric geometry, where the dimension of the torus is the same as the dimension of the space. Here we have a big torus. Okay, so that's kind of the direction we're heading. So I will talk about these cluster complexes, cluster algebras with universal coefficients, these Hilbert schemes, and yeah, that's going to be essentially the topic of this, the content of this talk. So the first two slides, the next two slides are going to be of kind of giving a very short introduction to the cluster combinatorics. They are not needed for the talk because, as I said before, the aim of this talk is to go beyond these combinatorics, but it will just maybe give a way for you to relate. I mean, to kind of appreciate the thing we're doing, because I mean, in cluster algebras, there's like always these combinatorics, and by passing them, we're actually well using this geometry and these torus actions. So okay, so what's a cluster algebra in general? It's just a commutative domain is equipped with a particular combinatorial structure. So first of all, and most important, a cluster structure, it's a structure, it's not a property. So if you have a ring or you have a variety, you have to exhibit a cluster structure. You have to put the structure on this object. So it's not a property. To build such a structure, you need this quiver, so this dots and arrows, this directed graph, and throughout the talk, n, it's going to be a fixed number. It's just the number of vertices of the quiver, and it's going to be the dimension of a lot of the spaces we will consider. And in order to get started, we need that these are not subgraphs of my quiver. This, okay, I will not elaborate on this. This is just something. I mean, we need this a little bit if you want to be in the cluster setting, so have a Triple algebra sitting in the back. A seed is going to be a pair of a quiver and just an n tuple of algebraically independent rational functions attached to the vertices of the quiver. So it's just the information of some, if you want, geometrically, it's just an information of a quiver and a torus. The torus will have these coordinates. I mean, and that's why we are asking them to be algebraically independent. So we depict quiver seeds in this way. First of all, the tuple here of coordinates are the cluster. Is the cluster, and here's how we depict seeds. So I have a quiver. In this case, would be a quiver with two vertices and just an arrow, and x1 and x2 are going to be the two rational functions that are attached to the vertex. Here's another example. These are going to be my 3 running examples, like a very small example, a first non-trivial example, second non-trivial example, and this somehow related to the first example, as we will see. So as you can see here, for example, the rational functions I decided to put in it, each vertex already have some labels. This will become apparent later because we want to relate to coordinate rings of varieties of interest. In this case, it's going to be the Grassmannians, and these are to be thought of as Klucker coordinates. These are going to be Klucker coordinates of Grassmannian of 2 planes in 5-dimensional space. Okay, so this is the combinatorics. This is actually the cluster combinatorics. This slide contains like the essence of cluster combinatorics. So you can, I will just go through them. You can decide to not to absorb them at all, because we're not going to use them. This is the thing that we will bypass using geometry. So anyways, for completeness, let's just say how to mutate a seed in a vertex V. Okay, so I mutate at the vertices of my quivers. So first of all, the rational function attached to the vertex V, it's replaced by another rational function. And well, it's just some formula, some binomial in between one monomial. So it's the variable you're replacing it by this quotient. And the 2 terms in the top are just indexed by the quiver. So here's where the quiver comes into play. The first monomial, it's a monomial indexing the arrows going to V, and the second monomial, the arrows going out from V. And we will call this an exchange relation, because what we're doing is actually exchanging this variable, well, this element of, this cluster variable by this cluster variable, or the element, the element of my cluster associated to the vertex V by a new one. Then what we're going to do, it's an operation on the quiver. So we compose arrows through B. As you can see, a path of length 2 like this gives a path of length 1 like this. So we just compose arrows, and we reverse all the arrows at B. So an arrow like this becomes like this. And then this procedure might generate 2 cycles. So we erase them because this was one of the conditions we have. So, okay, we just stay within the same class, and that's it. So that's the combinatorics we use to produce cluster algebra. So you start with a seed, then you have n different vertices, then you can produce n new seeds. And what we're going to do is iterate this process, look all the expressions we can form, and look at an algebra that we can build with those expressions. So that's essentially the cluster algebra. Let me just give you an example. So how do you look? How this look? If we're in example A and we decide to mutate in vertex 1, well, the quiver will just change the orientation because, well, you can just go back to the rules I gave, and we have a new rational expression. If we have the second example, we change, we mutate at 2, so we get another quiver. So look how the topology of the graph really changes. Here I have a whole, a cycle. Here I have no cycles. A new rational expression arises, and that's it. So most importantly, to actually find examples in nature, so find coordinate rings of varieties who have a cluster structure, what we will need is to declare some vertices to be frozen, namely some vertices in which we don't mutate. So let's go to example C, in which I start with this seed. Here, I'm thinking that all my expressions are going to be lying. All my symbols Pij are going to be elements of the homogeneous coordinate ring of the Grassmann of two planes of planes in a 5-dimensional space in its Fluker embedding. So this ring has just a presentation of, I have Fluker coordinates and Fluker relations. So I'm going to work everything is going to be appearing in this ring, and this is a cluster. I mean, these elements are algebraically independent, essentially because there's a torus in the affine cone of the Grassmannian with these coordinates, essentially. So when I mutate in this vertex, there's like an operation of the vertex. I mean, so I will declare all these guys sitting in the outside to be frozen. So I will just mutate at this vertex, and well, I will just do it, I will iterate doing mutation in this vertex and then in the other vertex. So when I mutate in the first vertex, I get a new rational expression that it's actually P2 in this ring. Why P2? P24, I'm sorry. Because, well, this is the way I exchange things. And if I put this guy here, what I just get, it's a Fluker relation. So what the guy that appears here, I'm sorry, the rational function that appears here could be either this or its short, its shortened version P24. And I mean, this is just schematics. I don't really expect you to really follow all the calculations or everything that I'm saying. Maybe at this point, if you're new with the theory, you can just look at how these drawings look. I mean, they look like very different graphs. They kind of change a lot, and there are arrows going everywhere. And okay, it's a bit of a mess, but there's something remarkable that at some point I come to the beginning. Okay. So that's why when I'm talking about frozen variables and about iterating this process. I don't know if there are any questions for the moment.
So, naively speaking, the derived category of the representations of these quiver will be related to that of the Grassmannian, or what's going on here?
Yeah, I mean, actually, yeah, that's a great question. There would be a categorification of the cluster structure. Actually, there would be a larger quiver like this. It will come at the end of the talk. So if I put even more arrows and some commutative relations here, actually the commutative relations are better expressed in a dimer model. So essentially, for example, doing this and doing this is the same because, well, this is like going by, like in this dimer model, like going in the direction of the white cycle and this in the red cycle. That's a commutative relation. This is an infinite dimensional algebra. Somehow Cohen-Macaulay modules over this algebra is going to be a categorification of the cluster structure. So yeah, like the big picture is like using representations of the quiver and adding appropriate relations and maybe appropriate arrows, I can categorize the cluster structure. So there will be like some sort of map from the objects of the Cohen-Macaulay models of this algebra. well, maybe of the boundary algebra, actually, not of the whole algebra, the boundary algebra, that it looked like another algebra. Those help me to categorify the cluster structure on this coordinate ring. So yeah, and I mean, there's always like some considerations. I mean, if I have no frozens, then I will consider the derived category of the quiver, and then do like some, if I don't have cycles, do an orbit category. If I have cycles, then I have to consider the Ginzburg-Digi algebra, and using the Ginzburg-Digi algebra and its derived category, I can categorize the cluster structure. So that would be like how to proceed in other cases in which you don't have frozen variables. Okay, so thank you for the question. Okay, so now the cluster algebra associated to a seed, it's just going to be the C algebra generated by all the elements, all the rational expressions that I just created by iterating this mutation to infinity. So it's very non-explicit object. So that's one of the main points of the theory. It's try to give global models of the cluster algebra, because from its construction it's completely non-explicit. And the approach of categorification that just asked, that Ernesto just asked, it's related to that, giving a global description of my cluster algebra. So, okay, let me just introduce some wording. Non-frozen generators of the cluster algebra are going to be the cluster variables, and the frozen generators are going to be the frozen variables. So in this case, let me just erase a little bit the junk. The things that are sitting here in the middle, these are the frozen, these are the cluster variables, and all these 5 things are the frozen variables, okay, that are present in every cluster. That's why they are frozen. So in the example, in my first running example, where my seed is just x1 goes to x2, my cluster, I can only generate 5 different rational functions that I put here, and my cluster algebra is going to be the one generated by this. This is going to be the coordinate ring of an Alfvén chart of del peso surface of degree 5 that you can verify if you want. So there's like a variety here sitting in the back that would be the smooth del peso surface of degree 5. In my second example, in which I have this seed, well, it's going to be related to the coordinate rim of the Grassmannian of 2 planes in a 6-dimensional space under some specialization. So all the Plucker coordinates of this form with consecutive indices will be 1, and I just have to specify x1 to be p12, x2 to be p35, and x3 to be p15. So for example, the cluster algebra associated to this guy, it's related to the coordinate ring of the Grassmannian 2,6. Finally, maybe already it's been almost explicit in my previous slides. In the third case, where I have like this quiver, my cluster algebra is just going to be the coordinate ring of Grassmann 2,5 in its Plucker embedding. Why? Well, the 5 exchange relations I can form are precisely the Plucker relations, and there are no more relations between these guys. So I have created all the generators of the ring, and I have created all the relations between them. So that's why I have this isomorphism. Okay. Well, so we're going to restrict ourselves to the finite type cluster algebras, or cluster algebras of finite cluster type. So these are those cluster algebras for which I only create a finite number of rational functions. So these are 3 examples of such. Here I only created 5 cluster variables. So okay, that's a well-defined term. Actually, what would be like a working definition? So I have a theorem by Fomin and Selevinsky in 2003. They show that AQ is of finite cluster type if and only if every connected component of the mutable part of Q is mutation equivalent to an orientation of an ADE linking diagram. So essentially, finite cluster algebras of finite cluster type are classified by ADE linking diagrams, or actually I should say that I'm working in a restricted generality. So if there would be for simplicity, I'm working in this generality. The paper is written in this generality in which all the thinking diagrams will appear. So there will not be a quiver. There would be some symmetrizable matrix or a valued quiver. And then there would be an analogous theorem in which all the thinking diagrams appear. So this theorem actually make apparent that these cluster algebras are fundamentally related to Lie algebras and to Lie theory, for example. Perfect. So why, I mean, that this explains why, for example, this cluster algebra, it's I mean, we can see this theorem for this guy. The theorem says that you only have to look at the mutable part of the quiver. And if that looks like a thinking quiver up to mutation, then you are in the finite type. And this is the case for this, right? Okay. So let me just go now to the universal coefficients. This is a notion introduced by Fomin and Selvinsky in 2006, in which they wanted to understand the family of all cluster algebras that are obtained when you just fix a quiver and then you're enlarging by putting like as many frozen vertices and arrows as you want. So is that class interesting in anything? In anything? So or can we say anything about that class? We fixed just like a part which we wanted to be fixed. Like it could be, you can fix, for example, something and a mutable vertex. This could be frozen, I'm sorry. And you ask yourself, okay, this is my quiver, and this gives a cluster algebra. What if I decided to throw 3 million more frozen vertices and many arrows between these guys? Is there any relation between these cluster algebras? And yes, there's a relation. There can be all obtained by a single one by specializing the values of the frozen variables. So that's the notion of universal cluster algebra that Fomin and Selvinsky pinned down. They proved their existence when we're in finite cluster type, and they show that actually it's obtained by adding as many frozen variables as non-frozen variables there are. So for example, in my first example, I have 5 cluster variables. So the universal cluster algebra associated to this will have 5 frozen vertices, and so on. And this is the kind of universal property that they obtain. For example, if I start in example 3, and I just decide to look at the class of all the cluster algebras obtained by enlarging this quiver by throwing frozen vertices, well, the universal guy, it's going to be obtained by throwing these 5 new vertices that I put here, and compute the cluster algebra. So it will look like this. So maybe like in some way, if I have any quiver, exchange relations are going to look like this, but maybe the things appearing in red will be different. And this guy has the magic that we can specialize the red things to any other thing obtained by putting more frozen vertices to recover the same exchange relations. So in some sense, these exchange relations are simple enough or complicated enough to recover everything. Okay, so that's the classical part of cluster algebras, and this object, this universal cluster algebra, is the one that we would like to understand using the formation theory of the cluster complex and Hilbert schemes. So I will move to discussing cluster complexes. Maybe, are there any questions so far? Okay. Okay, so what's the cluster complex? The cluster complex is a simplicial complex that's going to have, well, a set of vertices and a set of simplices. So the vertices are just going to be the cluster variables, namely these rational expressions that I created by mutation and that are attached to the mutable vertices. And a simplex, an ith simplex, is just going to be a collection of cluster variables that sit in the same seat. That when I look at all these pictures of quivers with variables sitting on them, well, I see the same variables, these variables sitting in the same quiver. Okay, so these are going to be we will call this compatible if they sit in the same seat. Okay, so maybe remarks, there are several ways to describe this cluster complex. One very transcendent, very important, given by Fomin and Selevinsky, using combinatorics on root systems of the corresponding Lie algebra. We can use homological algebra in the category of representations of the quiver with the potential. We can use topological models, or we can use cluster algebras. And today, well, this definition that I just gave, it's the one that uses cluster algebras, right? I mean, it's just how I define for you. Let me just give you a flavor of how this complex would be obtained using topological information. For example, if I'm in this case, in example B, the same cluster complex is going to be dual to this Stashev polytope, encoding the triangulations of the six-gon, the topological triangulations of a six-gon. Okay, so for other types, there would be similar models, like using topology of, well, like the triangulations of a surface, for example, right? And here, dual means that I replace like a simplex of dimension I by its codimension. So this would be like the guy. So the picture at the beginning of the talk. This is a beautiful theorem by Fomin and Selevinsky that's telling us that essentially topologically all these complexes of finite these cluster complexes associated to cluster algebras of finite to cluster type are just spheres. So if you want, a cluster complex of finite cluster type is just a particular, very particular subdivision of the sphere into simplexes, so a triangulation of this of a sphere. And it's an if and only if. So that's also nice. When I'm beyond the cluster finite case, well, I will obtain stuff that actually is not compact. And the theorem by Giovanni Cerulirelli, Bernard Keller, Labardini Fragoso, and Plamondon is that this cluster complex only depends on the mutable part of Q. Okay, so in the examples, my first example was like something like this, and my cluster complex is going to be this. So I was just trying to explain maybe when everything went wrong, that the cluster complex of this example and this example are the same, just illustrating the theorem of this set of authors. And well, this is going to be the cluster complex on type A3, which is the dual complex of this guy. So maybe the main guiding question of this talk is if we can recover A from its cluster complex, and the answer, of course, it's no, as this example suggests. We have the same cluster complex for example, running example A and C. However, well, they are different. I mean, they correspond to coordinate rings of affine variety of even different dimensions. So the answer is no. But the answer we will give is that it's almost possible to recover the cluster algebra from the cluster complex. We just need a bit more of information and use deformation theory. And the bonus is that this idea can be obtained beyond the cluster case. Okay, so let's go now to the geometry. I'm going to be precise of what do I mean by this deformation theory. So I will consider a scheme Y, and it's going to be a space Z. So why do I say space? Most likely I will have to, when I talk about deformation theory, I will have to go beyond the category of schemes. This might be formal schemes, for example. So Z in general is going to be a formal scheme. A deformation of this scheme Y over this base Z, it's a flat morphism from a larger scheme Y, such that the other Y, the original scheme, appears as a fiber, right? So it's just a flat morphism. We're admitting Y as a fiber. What's the picture to keep in mind? For example, if my variety it's this the xx and x the y and xx axis, then I can consider this this family xy minus t as a subvariety of affine space of dimension 3, and well, this is going to be a scheme over a t over affine space of dimension 1 with coordinate t, and this is going to be a fiber of this scheme. So any other fiber is going to be a deformation. Okay, so that's like kind of the picture to keep in mind. And the maybe a very important theorem of the sextet by Grothendieck is whenever I have a projective scheme inside an n-dimensional projective space. Here, actually, I'm working over C, but this theorem works over any field. Then there exists the following. There exists a Hilbert scheme, which is just the moduli space of closed subschemes of Pn with the same Hilbert function as Y, and a universal family. So this is going to be there's going to be this family over this base, a flat morphism, and points here are represented by subschemes of the projective space with the same Hilbert function. Let's call the class represented by y prime to be y prime brackets, and then the fiber over this point, it's just the variety it parameterizes. And if you don't remember what's the Hilbert function, well, let me just tell you that since we're working with a projective variety, we will have a C star action on the cone, on the affine cone of this variety. So we will have a graded ring, Rn, and this ring would be actually positively graded. And the Hilbert function, it's just the function that remembers the dimension of every graded base. Okay, so we'll have a generalization of this, where when I don't have only a grading by Z, but I have a grading by any other group. These are the multi-graded Hilbert schemes. These are studied by Hyman and Strumpfels at the beginning of the years 2000. So here, if we start again with a projective variety inside a projective space, well, a polarized projective variety, say, and we assume that we have a torus acting on the affine cone of Y, then, well, since we are dealing with a projective variety, I will also have a graded ring. But then this action of this other torus is going to give me another grading on the ring. But the grading now is going to be given by the character group of this group H. And well, there will be a multigraded Hilbert function that goes from the character group of H to the n. That, well, this just gives me the dimension of Rn. Okay, so it's just exactly as before, but we were potentially acting by different groups. And Hyman and Strumpfels prove that this classical theorem by Grothendieck also extends to this setting. So I will have a multigraded Hilbert scheme that would be a moduli space, parameterizing H invariant subschemes, or where in the affine space where the affine cone lives, with the same multigraded Hilbert functions and Y. So it's important to go to the affine space here in order to be able to act by this torus, just as here we have to go to one dimension higher to have this sister action, right? So that's why we have changed it here, the space. Okay, so this is my background on deformation theory. Essentially, well, it's just recalling this existence of these Hilbert schemes and what do I refer by them, and maybe drawing your attention to this multi-graded version, but it's a little bit more recent. So what's the spaces we're going to deform, or are going to be, well, either a spec of the cluster algebra or a spec of the Stanley-Reisner ring. That's going to be a ring. It's going to be another ring that can be obtained from the cluster complex. So if I start with any simplicial complex, I can consider the Stanley-Reisner ideal of this complex. This is just going to be an ideal living in a polynomial ring with as many variables as vertices I have in my simplicial complex. And the generators, it's going to be a monomial ideal. The generators are going to be given by non-phases or non-phases of my simplicial complex. So whenever I have something that's not a phase, that gives me a generator of my ideal. The Stanley-Reisner ring is just going to be the quotient ring of the corresponding polynomial ring by the corresponding ideal. And well, the Stanley-Reisner scheme is just going to be spec of this or crush of this, because of course this is a homogeneous ideal. It's just generated by monomials, so it has a projective scheme, and somehow this projective scheme looks essentially like your cluster. I mean, it's like it would be like some sort of hyperspace arrangement in a projective space that looks like your simplicial complex. So that's an algebraic avatar for your simplicial complex. So example, well, I'm considering this as a lot. So for example, here 1, 4 is not it's not a phase of my polytope or of my simplicial complex. I'm sorry. So that's why I have this generator, and the other 5 are going to be the other 4 are giving these other 4 generators. An important operation that I can do in simplicial complexes is the join. It's just a simplicial complex obtained by just matching all the corresponding phases. And well, this operation translates to tensor product at the level of rings. So direct product at the level of varieties. Okay, so now we have finally all the ingredients so that I can say something interesting to you, hopefully. So first of all, I'm going to just say that this universal cluster algebra is actually a deformation. So the first thing we show is, okay, this universal cluster algebra actually has the structure of a CT1 to TP module here. T1, let me recall, T1 to through TP are frozen variables associated to a uniform. Okay, so as I said before, this cluster algebra with universal coefficient is obtained by throwing just some new frozen vertices. Well, each frozen vertex has a frozen variable, and these are the generators of my polynomial ring. So this is so geometrically, this variety with universal coefficients, it's a scheme over this affine space. And the first theorem, it's like, okay, I can consider this as a family of deformations of both the Stanley-Reisner scheme or of the cluster algebra. So first of all, pi is a flat morphism, and the inverse image over, like the special fiber, it's going to be the Stanley-Reisner scheme. So this might look like very, how to say, intuitive, because when I have like the exchange relations like this, taking all coefficients to 0 is just, well, killing all these terms. So I'm just setting these monomials to 0, as these are going to be, in this case, the monomials appearing in my Stanley-Reisner ring. The problem is, like, it's in the cluster algebra, there are not only these exchange relations, there are more relations than that. So you have to be careful. I mean, a student can very easily say that this is, for example, trivial without noticing that, well, there are more relations than the exchange relations. So that's kind of the main point. So this theorem 1 says, like, okay, what we see in the exchange relations is actually a general fact. So now let me talk about which are the tori that are acting on all these spaces. So if I have a cluster algebra of finite cluster type, we have a non-explicit presentation given by a polynomial ring with as many variables as, I mean, this has a huge set of variables. I will have a variable for each cluster variable and a variable for each frozen variable. And so this polynomial ring has a map to A, surjective map. I just send every variable to the corresponding generator. Well, the kernel of this map will give rise to a presentation of my algebra. This is a non-explicit presentation. Nonetheless, what we obtain, it's an embedding called the cluster embedding of the corresponding space. So for example, there are some examples here related to Grassmannians. For example, if I have Grassmannian 3,6, the cluster embedding and the Plucker embedding are going to be different, for example. So it's a different embedding that's obtained by cluster algebras. So in this embedding, I just consider, well, the torus of the corresponding space. Okay, so this is just the torus of the ambient torus. And H is going to be the maximal subtorus fixing this affine variety that I embedded here. So the cluster variety or the partial compactification of the cluster variety. So, okay, these are things that I can define. Well, very importantly, I want to be in the case in which A corresponds to the cluster structure of a projective variety. So what I would like it to be, it's that this cluster algebra is set graded and that the degree of every cluster and frozen variable is positive. This is kind of technical conditions, but actually those are very natural conditions in the examples arising in nature. So what I'm going to consider is this Hilbert scheme. So it's going to be maybe here I have to put not A. Let's say A. This is whenever I just my notation is A. It's going to replace a spec of A because here I have to put some space, but I just put an algebra just to have small notation. Anyways, so what's this Hilbert scheme parametrizing? It parametrizes H invariance of schemes on this in this ambient affine space with the same multigraded Hilbert function as a spec of A. Okay, so by the theorem of, I mean, I need this positively graded. I need this for this Hilbert scheme to have nice properties using the theorem by Hyman and Sturmfeld. And okay, there's going to be an action of H, well, this is a trivial action. The action here is going to be trivial, and well, the action here of H is interesting. But the big torus is also acting everywhere. That's important. So I also have here the action of T. Well, at least here, well, this is just a point, and here, and this is going to be H invariant deformation in the sense that this is an H invariant Cartesian diagram, and it's going to be, yeah, just H invariant. So the second theorem, it's relating this map with this map. Okay, so this map from the cluster algebra with universal coefficient is, as I just said in the beginning of the talk, a restriction of the of this universal family over this Hilbert scheme. So what's new in this theorem? Well, this interpretation of the base as some part of this Hilbert scheme. Actually, this has an action of H. Well, I'm sorry, it's H invariant. And actually, this base can be obtained by applying this big torus action to the point of, this is going to be T applied in the space, in the point of the Hilbert scheme corresponding to the spec of the cluster algebra, and it's going to be a partial closure. So, so yeah, like exactly the theorem I alluded in the beginning. So this map obtained from cluster setting, it's just more geometrically. If you want another way of saying of explaining this theorem, is like actually cluster algebras with universal coefficients are just parts of universal families over Hilbert schemes. So that's our interpretation of our geometric interpretation of the cluster algebra with universal coefficients, just as this restriction of the universal family over this scheme into some torus orbit closure. The counterpart, it's how do I build this deformation actually just from the most degenerate fiber. So the most degenerate fiber is the Stanley-Reisner ring of the cluster complex. So it's a counterpart because for this you need somehow you need the existence of this of this universal family. Here you are constructing it from the most degenerate part. And well, if A has enough frozen variables, I don't want to say what's this. It's just some assumption, some hypothesis that can be made combinatorially. Then there's a canonical T equivariant, H invariant, semi-universal deformation of the Stanley-Reisner ring that well, this is pi, like this cluster algebra with universal coefficients can be just tied up with the most general fiber as a semi-universal, as a canonical T equivariant H invariant semi-universal deformation. What's T equivariant? Well, this map is T equivariant with respect to the action of the big torus, and semi-universal means that any other deformation of this degenerate fiber, it's obtained non-canonically via pullback of this from this deformation. So the upshot is that in order to recover so maybe this is like really the upshot. In order to recover the cluster algebra with universal coefficients, and in particular the cluster algebra itself, what I would need is just the cluster complex and the m degrees of the cluster variables, because that's the only thing of pieces of information that we need to recover this map. So that's kind of the long story short. I had some slides presenting some ideas of the proof. It's essentially saying that okay, the main technical tool that we consider was the cotangent cohomology of the Stanley-Reisner ring, and we have like a very precise description of the first order deformations and of the seconds and the space of obstructions, which is the second cohomology ring of this. Well, the second cotangent cohomology, and well, we showed that these cluster complexes are actually unobstructed whenever I'm in this setting of quivers. When I go beyond the setting of quivers, the cluster complexes are going to have obstructions, and the deformation spaces will be infinite dimensionals. So there's versions of this theorem for say cluster algebras of type B, C, the non-simply late, but they have to be adapted since we have obstructions in that part, and the deformation space is infinite dimensional. So another interpretation of this is that these are actually the deformation directions. We only have P. I mean, the first order deformation space has dimension P, and this is the tangent space at some point of the deformation space. Okay, so we also have a nice control of something called the Kodaira-Spencer map. I don't have the time to explain this. Maybe just let me close my talk saying what's the slogan of the talk. Well, if you are, for example, willing to program this, it's possible, because these semi-universal deformations that I talk about have a package in Macaulay too. So actually, you can communicate very easily with them and just get like explicit expressions for whatever complex you want. So it sounds kind of like these Hilbert schemes, like okay, sound a bit theoretical, but you can also have equations for them if you want. And the second bonus is that we can produce nice varieties beyond the clusters case. And here the term beyond the cluster case is replaced by tau tilting finite algebras. So this will be some kinds of associative algebras in which we have a similar way to construct like an analogous. We have a way to construct something analogous to the cluster complex using the homological algebra of the model category of the algebra. And well, they are I mean, it's understood when we obtain finite complexes. So, for example, what would be like some schematics of what I just said? If I start with this associative algebra, then my theorems ask to have enough frozen variables. So this condition of having enough frozen variables can be better seen in this example as, well, you have to throw more information to make the algebra more interesting. And well, you have to find also like the nice algebra you find. And if you apply your deformation theory techniques, you obtain this variety. So this would be an algebra that is not of cluster type. This would be beyond the cluster setting. We don't know like how to describe the enough frozen like in terms of an associative algebra, but we can just do it by means of algebraic geometry. So we still don't know what's going on here, and we can produce like nice algebras. In this case, SO2 orthogonal bilinear forms in 10-dimensional space. So okay. Let me just finish here, and thank you very much for your attention. And sorry for the problems.
Any questions? So, how does this connect with these mirror pairs that you used to obtain now? Do you obtain more mirror pairs generalizing from this cluster algebra?
Well, you just get one variety. So, for example, here, what I explained in the very beginning would just be one arrow here, right? So essentially, here you can put, if you want, a spec of A or a spec of a univ. All of these will be instances of a single variety you can build. And to obtain the other variety, I mean, in the cluster case, you use a construction by Fogh-Goncharov, in which, I don't know, I mean, this has an atlas of tori. So this is obtained by gluing dual tori using dual maps somehow. So at least we have this part. And well, there's other people like Pierre-Guy Plamondon and Hugh Thomas and Nimar Hamed and that are actually trying to build like some variety associated to the other part. So let's say our approach will just accomplish one arrow, and it's still not yet clear what should be the other arrow. I think it's just work in progress by parts of the community.
Okay. Any other questions? Well, thank you very much, Alfredo. For a very nice talk, and we will continue.